Imagine you are in an F1 pit stop. Every single millisecond counts. One wrong move, one hesitation, and your race is over. That is exactly what a Cambridge IGCSE physics practical exam is like. You weren't just tested on what you know, you're tested on your unyielding precision under intense time pressure. Let's skip the fluff. Today, we're locking down the exact method marks that most students carelessly throw away. Think about it. Misidentifying a single variable in your exam is a devastating time penalty. It can literally cost you an entire grade boundary. You wouldn't want a mechanic grabbing the wrong tire, right? Well, your Cambridge examiner doesn't want to see you fumbling your independent and dependent variables. But why is it that a staggering 80% of students lose these easy marks, especially on core practicals like the critical angle experiment? Simply put, it comes down to a fundamental lack of exactness. We are going to look at the painful mistakes that ordinary revision completely ignores. Just take a look at this. On the left, we have a classic 0-mark answer, giving some vague description of what was changed and measured. Now look at the right, a full-mark response that uses exact examiner-approved terminology. Ordinary revision fails because it just tells you to memorize textbook definitions without actually showing you how examiners look at your data on the mark scheme. When you're faced with a data collection question, you usually end up picking one of three doors. Door 1 is guessing. You're just hoping your everyday language is good enough. Spoiler alert, it never is. Door 2 is memorizing. You spit out a robotic definition that doesn't actually fit the specific experiment sitting right in front of you. But door 3, that's the framework. And that is exactly what we are going to master today, so you can unlock those exact Cambridge method marks. Okay, let's dive right into this. The independent variable. This is simply the one variable you consciously choose to change first to test its effects. If you're planning an experiment, this is literally the very first decision you make. You are in the driver's seat here. You dictate this value. It's the core input of your entire investigation, and clearly identifying it right away signals to the examiner that you truly understand the fundamental design of the practical. And that brilliantly illustrates the flip side. The dependent variable is what you are actually measuring or observing when you change that independent variable. Think about measuring the extension when you stretch a spring with a force. In that classic Hooke's law setup, the force or the load you apply is your independent variable. The extension that happens as a result, the actual data you are closely observing and writing down in your table, that's your dependent variable. One relies entirely on the other. Once you've identified those two, you know what affects what. Anything else that must stay exactly the same is your control variable. If you don't lock down your control variables, your entire experiment just falls apart. It becomes a completely unfair test. You absolutely must be able to explicitly state which factors are being held constant, so the examiner knows your dependent variable's results are purely due to the independent variable you changed. To build a top-band answer every single time, we apply this 4-step framework, so the examiner literally has no choice but to award you full marks. First, you state the concept. Second, you pull specific evidence or data directly from the experiment. Third, you apply scientific reasoning to connect the two. And fourth, you wrap it all up tightly in the exact examiner wording they are actively scanning for on their mark scheme. It's systematic, it's repeatable, and honestly, it's bulletproof. Now, in just a moment, I'm going to show you the hidden examiner clue regarding continuous versus discrete data that changes the answer completely. But first, you need the framework that makes that clue super obvious. Because simply knowing your variables isn't going to be enough if you fundamentally misinterpret the actual numbers you are recording. See, you absolutely must be aware of the nature of the data you collect, which always falls into one of these 3 specific categories. First up, categorical data. This is sorted by names or types, things that can't be mathematically ordered, like different types of materials. Then we have continuous data. This can take absolutely any numerical value within a certain range, like a temperature reading of 24.5 degrees. And finally, discrete data. This can only take specific certain values. Let's do a quick test on this. If you are looking at the number of protons in an atom, which type of data is that? Take a second and really think about it. Based on the definitions we just covered, are we dealing with a continuous range where any fraction is possible, or are we locked into specific boundaries? Exactly, it's discrete. Why? Because you can only have whole numbers of protons. You can't exactly have half a proton. Now, this might seem incredibly basic, but misidentifying this on an actual exam dictates how you draw your graphs, how you interpret your lines of best fit, and ultimately whether or not you secure those crucial analysis marks. Conversely, think about a ball drop experiment. If you measure a ball's bounce from a 1-meter drop and a 3-meter drop, You can easily estimate the 2-meter mark. That is because the drop height takes a numerical value within a continuous range. This is continuous data at work. Since the drop height can theoretically be any value, like 1.5 meters or 2.1 meters, you can safely interpolate between your known data points. Identifying continuous data tells you that drawing a trend line is mathematically and scientifically valid. Now, let's see how this all comes together. We are going to apply everything we've learned to a real Cambridge Worked example. Here we have a setup with semicircular blocks of different materials. We've got light rays entering the flat side of blocks made of glass, perspex, and so on. The entire goal of this practical is to find the critical angle as the light emerges into the air. Let's view this through our examiner framework. I want you to pause and predict right here. Based on our framework, what is the independent variable and what is the dependent variable in this specific light experiment? Look closely at the setup. Ask yourself, what is the experimenter actively swapping out on the desk? And as a direct result of that swap, what numerical value are they trying to read off their protractor? Okay, so here is the crucial point. You have to avoid a painful, vague answer if you want to secure those method marks. Saying something like, I changed the block and measured the light, gets you absolutely 0 marks. It shows 0 scientific rigor. But look at the top band answer. It explicitly states, independent variable is the material of the block and the dependent variable is the size of the critical angle. Bam! That is exactly the terminology the mark scheme demands. Let's move to our final check and see how all of this builds together. The material of the block is categorical data, and the size of the critical angle is continuous data within a range. You have completely mapped the DNA of this practical. Now, here is that secret insight I promised you, the one that changes your entire strategy. Because the independent variable is categorical, like glass, plastic, or diamond, you would likely present this in a bar chart, not a scatter graph. Understanding this exact connection is what separates average students from top-tier candidates. So, you've crushed this lap, you've secured these variables marks, but leaving right now means you are completely exposed to the common question type traps that literally ruin grade boundaries. We've completely optimized your pit stop for data collection, but out on the track, the examiners are using highly specific command words designed to trip you up if you aren't paying incredibly close attention. Before you celebrate, ask yourself this. If an examiner asks you to evaluate rather than describe your data, do you actually know how your framework changes? To unlock door number 2 and avoid those devastating exam traps, your next lap requires the next explainer. Watch it immediately and subscribe to our YouTube channel, Ace the Exams, at acexams_IGCS to excel in your Cambridge examinations.